Hello everyone, and this is the third lecture for machine learning techniques. And today we are here to talk about regression. Supervised learning in machine learning is majorly made up of two components. One is regression and one is classification. So what is regression? Regression in short terms is basically prediction. You try to understand the patterns of the data and you try to predict what is going to happen with the data if it is going to follow the set pattern. And what is classification? As the name says, classification is trying to categorize or trying to find the difference between data in order to give a yes or no answer. Now diving into types of regression, we are starting with simple linear regression. So what is this? It is basically a model that finds the best straight line relationship between one input feature and one output value. All of you know that a straight line is y equals mx plus c, where the input is x and the output is y. So there's only one parameter, so it's going to be a straight line. So basically, you want to understand the data as a form of a straight line and try to predict accordingly. Let's say your input x is years of experience, output y is salary. So effectively, as experience increases, your salary does tend to increase. Let's look more in the next slide. How does the simple linear regression work? So as I said earlier, we usually follow y equals mx plus c because simple linear regression is in the form of a straight line. So here it's in different forms. This y equals to beta naught plus beta 1 into x. So beta 1 obviously being the slope of the line and beta naught being the intercept. So how does the data that we have fit into this straight line? For every point, obviously we're not going to have all the points in a straight line. There's going to be a bit of difference. So initially we're going to draw a line and then we try to find the error between the line and the different points. So as we train again and again on data, on multiple points of data, we aim to minimize this error as much as possible so that we get the ideal regressional line. And following this line beyond the data, since the data is here, when we try to extend it beyond the data, that is where you get into prediction. So you can predict that, as x-axis increases more and more and you get more number of points, it is going to follow this pattern, which is along the straight line. This is simple linear regression. Now you all may be thinking, in simple linear regression, we have only one input parameter. But in real world, we have thousands of parameters. How do we do this? Very simple. There's another one called as multiple linear regression, where there are more features leading to the model getting more amount of data or information leading to better predictions. So very simple, where we have y equals to mx plus c or y equals to beta naught plus beta 1 into x. Here you have y equals to beta naught plus beta 1 into x1 plus beta naught into x2 and so on up to beta n into xn. Again, here also is the same, where you have the error function and you try to reduce the error across all the points. Now, what is the drawback of this multiple linear regression? The major drawback is overfitting because of large coefficients. Now, because we have so many features, the model just learns based on the data and it does not know how important each feature is. Because of which, if you train it for a long period of time, it is very much possible that features that do not really affect the data as much in real time, the model may perceive it to be actually very important. Because of which those non-important ones may have very, very large coefficients and just small changes in those, even though in actuality it does not affect the data or the output as much, the model has huge variance, because of which the model becomes very, very unstable. One very common issue is multicollinearity, where let's say there are two features, where here the example is given as house size in square feet and house size in square meters. Effectively, both of them are the same data, but just in different units, which means ideally both of them should be having the same weight. But when you train, it is very much possible that these two do not have the same weights, because of which this may cause problems in the output and give a wrong result. Now, how do we solve this problem of huge coefficients because of overfitting? In comes ridge regression. So basically here we add a ridge penalty term to the error function. As we know, regression works based off minimizing the error function. So this here is the error function, and then additionally to it we have something called a ridge penalty term. So basically, if any coefficient becomes too big because of overfitting, this ridge penalty term makes sure that it reduces or does not allow it to become as big and distributes the weight of the bigger one across the other features, because of which the algorithm makes sure that all of the features have weights which are smaller. All of this in the end leads to a more stable and reliable model, especially when features are correlated. So far we have heard or learned in regression that we try to predict the model's outputs based off the data that we have given, may it be through simple linear regression or multiple linear regression or even ridge regression. So basically the output of this is going to lie based off the data, which means the output is continuous. So it's going to be lying between minus infinity to plus infinity. Now, what if I want to segment my data? What if I want to classify my data into yes or no or a 0 or 1 decision? Will a student pass or fail? Is an email spam or not spam? Will a customer buy a product? Here, there's no use of using regression, which is only a prediction. We want to classify. How do we do this? This is solved using logistic regression. So far in regression, we have only looked at prediction or trying to find out the line. Here, we try to find out the probability. How is this done? So it starts like a linear model to calculate a score based on the features or the weights. And then this score that comes is fed into a sigmoid function, which gives a S-shaped curve and always lies between 0 and 1. So accordingly, we can try to find the probability of which side does the data lie on. As we spoke earlier, the sigmoid function isn't a yes or a no, it's a probability. For example, let's say a student wants to pass based off number of hours he studied. So the input, let's say, is 8 hours, and the logistic model gives 0.92, which means it's a 92% probability the student will pass. So usually we set thresholds for things like this. In general cases, the threshold does lie at 0.5, because of which we can simplify it as greater than 0.5, it is 1 or pass, or lesser than 0.5, it is 0 or failure. In short, to summarize what we've looked at in this lecture, we have looked at various models, starting with simple linear regression, which is a regressional type, where we want to predict a number or a continuous series of numbers just from one feature by finding the best straight line. And next, multiple linear regression, where we try to predict a number or many numbers from multiple features and try to find the best plane or hyperplane. Next, moving on to ridge regression, where it improves upon multilinear regression because of it having huge weights or coefficients. It penalizes these large coefficients to prevent overfitting and better results. And finally, logistic regression, which even though is called regression, is more of a classification problem where we try to predict a category if it's yes or no by using the probability which is given to us using a sigmoid function. Thank you everyone, and I'll see you in the next lecture.